Section 9.2, Estimating a Population Mean. We will look at these 5 objectives in this section. Objective 1, we want to obtain a point estimate for the population mean. A point estimate is the value of a statistic that estimates the value of a parameter. Remember that a statistic is a measure from a sample, and a parameter is a measure from a population. For example, the sample mean x bar is a point estimate of the population mean mu. So let's look at an example. We want to look at computing a point estimate. Pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represent the weights in grams of 17 randomly selected pennies minted after 1982. We want to treat the data as a simple random sample. Estimate the population mean weight of pennies minted after 1982. So the sample mean, x bar, will come from adding all of these values together. So we would start with 2.46, 2.47, all the way up, counting every value up to 2.45. We add those all together and we divide by the total, which in this case is 17. So here we see we've added up all of those values in the calculator and we get 41.89. We want to now divide by 17. And we get approximately 2.464. And so then this value for x bar, or the sample mean, is the point estimate. And it's the point estimate of our population mean, mu, and it's going to be our 2.464 grams. Objective 2, state properties of students' t-distribution. Suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t, given by this formula here, follows students' t-distribution with n-1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation, and the value of n is our sample size. So let's look at some properties of the t-distribution. The first one is that the t-distribution is different for different degrees of freedom. Secondly, the t-distribution is centered at 0 and is symmetric about 0. Third, the area under the curve is 1, and the area under the curve to the right of 0 equals the area under the curve to the left of 0, which equals 1/2. 4, as t increases or decreases without bound, the graph approaches but never equals 0. 5, the area in the tails of the t-distribution is a little greater than the area in the tails of the standard normal distribution, because we're using s as an estimate of sigma, thereby introducing further variability into the t statistic. 6, as the sample size n increases, the density curve of t gets closer to the standard normal density curve. This result occurs because as the sample size increases, the values of s, our standard deviation, get closer to the values of sigma, the population standard deviation, by the law of large numbers. In this figure, we see the t-distribution for the sample sizes n = 5 and n = 15, along with the standard normal density curve. So if we're looking at the picture from the top here, the first curve is the standard normal density curve. Next underneath it is the curve for the t-distribution with a sample size of 15, and then underneath that we have the one with sample size of n = 5. Objective 3, determine t-values. The notation T sub alpha is the t-value such that the area under the standard normal curve to the right is alpha. And here we see it in this picture. So let's look at an example. We want to find the t-value such that the area under the t-distribution to the right of the t-value is 0.2, assuming 10 degrees of freedom. So that is, we want to find t sub 0.20 with 10 degrees of freedom. And here's a picture of what we're looking at. So the area to the right of the t-value we're trying to find will be 0.2 or 0.20. So we look at our table 6 for the t-distribution. And we're looking down the degrees of freedom at 10 here. And across the top, the area in the right tail was 0.20. So we see here our value is 0.879. So our t-value, t with a subscript of 0.20, is equal to 0.879. Objective 4. Construct and interpret a confidence interval for the population mean. So there's some things that need to be true before we can construct our confidence interval. First, the sample data needs to come from a simple random sample or a randomized experiment. Then the sample size needs to be small relative to the population size. So little n needs to be less than or equal to 5% of capital N, which is the population size. Next, the data come from a population that is normally distributed, or the sample size is large. So our confidence interval for mu is then given by these formulas for the lower bound and upper bound. Notice they're very similar to what we use for proportion, except now we have x bar, our sample mean, minus our t value, sub alpha over 2, times our sample standard deviation divided by the square root of n. And for the upper bound, we have the same formula, except we're adding this time. And remember that our t sub alpha over 2 is the critical value with n minus 1 degrees of freedom. So let's look at using simulation to demonstrate the idea of a confidence interval. In this example, we'll use Minitab to simulate obtaining 30 simple random samples of size n equal 8 from a population that is normally distributed with mu equal 50 and sigma equal to 10. Then we want to construct a 95% confidence interval for each sample and see how many of the samples result in intervals that contain our mu equal 50. So in the next slide, we'll see our 30 simple random samples and our 95% confidence intervals for each sample. And we're going to highlight the ones that do not contain our population mean of 50. So here we see in the first 15 samples with our 95% confidence intervals that all of them contain the value of 50 between the lower bound and the upper bound, except for number 8, highlighted here. And here's the remaining 15, which gives us all 30. And we see again that all of them contain the value of 50, except for number 28. So we take note that 28 out of the 30, or 93% of the confidence intervals, contain the population mean mu equal 50. And that value of 93% just came from calculating 28 divided by 30 and rounding. In general, for a 95% confidence interval, any sample mean that lies within 1.96 standard errors of the population mean will result in a confidence interval that contains mu. Whether a confidence interval contains mu depends solely on the sample mean x bar. So now let's look at actually constructing a confidence interval. In this example, we want to construct a 99% confidence interval about the population mean weight in grams of pennies minted after 1982, we assume that we have a sample standard deviation equal to 0.02 grams. So for 99% confidence, our T sub alpha over 2 will be equal to T sub 0.01, remember taking alpha equal to 1 minus our 0.99, and then we divide that by 2, so we have a T of 0.005. And our N value here was 17. And recall from our earlier example that we calculated our mean X bar to be approximately 2.464. So to locate T, let's look at our chart. And for degrees of freedom, n minus 1, we have 16. And our 0.005 is the area in the right tail. And so we see we get a value for T equal to 2.921. So we can calculate our lower bound, which is equal to our X bar minus our T value times our standard deviation divided by the square root of n. So we have 2.464 minus our 2.921 times 0.02 for S divided by the square root of 17. And we get a value of about 2.450. Now let's calculate the upper bound. Remember, that's the same formula except this time we're adding. So we have 2.464 plus 2.921 times 0.02 over the square root of 17. And we see that we get then a value for our upper bound of about 2.478. So then we're 99% confident that the mean weight of pennies minted after 1982 is between our lower bound of 2.450 and our upper bound of 2.478. So let's look at doing the same example on the calculator. When we're given raw data, we can enter those data values into a list. So we press Stat and hit Enter on Edit, and we type our data values into the list. Once all the data values are in the list, we press Stat, arrow over to Tests, and arrow down to number 8 for the T interval, and hit Enter. If the data are raw, then we highlight Data, and we make sure that the list is set to L1 and the frequency is set to 1. But if you know the summary statistics, you already know what X bar is and you already know what S is. In that case then, you would highlight Stats and then enter those values there. So I'm going to go back to Data for this example. And we want to enter our confidence level under C level. In this case, we wanted a 99% confidence level. Then we arrow down to Calculate and highlight it and then press Enter. And then the calculator gives us our lower bound and our upper bound for our T interval. And notice that it also calculated X bar and our sample standard deviation. Objective 5, find the sample size needed to estimate the population mean within a given margin of error. The sample size required to estimate the population mean mu within a level of confidence, 1 minus alpha times 100%, with a specified margin of error E, is given by n equal to our critical value for Z, alpha over 2, times our sample standard deviation divided by the margin of error E, and that whole quantity is then squared. And remember that n is rounded up to the nearest whole number. So let's look at this example back to the pennies. We want to know how large a sample size would be required to estimate the mean weight of a penny manufactured after 1982 within 0.005 grams with a 99% confidence, assuming that the sample standard deviation S is equal to 0.02. So our Z sub alpha over 2, critical value for Z, with a 99% confidence, we can look at this table here and see that we need to use a value of 2.575. We were given S is equal to 0.02. And remember that E, you're always going to look for the word within. and we see that E then is 0.005 grams. So our formula for the sample size is going to be equal to our Z value times S divided by E, that whole thing squared. So I have 2.575 times 0.02 divided by 0.005 quantity squared. So here we can see how to type it into the calculator, and we hit enter. We get a value of 106.09. But remember that we must always round up. So we round up, and our minimum sample size then would be a value for n equal to 107. Section 9.3, putting it together, which procedure do I use? We want to determine the appropriate confidence interval to construct. Remember that we've only looked at two different types of confidence intervals. So the first question we need to ask is, which parameter are we estimating? If we're estimating a proportion, provided that n times p hat times 1 minus p hat is greater than or equal to 10, then we construct a confidence interval for p. If we're looking at the mean, mu, then we ask ourselves, is our value of n greater than or equal to 30? So is our sample size large enough? If it's not, then we need to make sure that the data come from a population that's approximately normal with no outliers. If not, then we can't do these methods we've learned. If it is, then we compute the t-interval. And if our sample size is large enough, then we simply compute the t-interval. So in this example, we want to identify which type of confidence interval to use. First, a simple random sample of size n equals 785 adults was asked if they follow college football. Of the 785 surveyed, 275 responded that they did follow college football. Construct a 95% confidence interval for the population proportion of adults who follow college football. Here we see that we're looking at a confidence interval for the proportion. So we're going to do a confidence interval for p. In this next example, a simple random sample of size n equal 12 is drawn from a population that is normally distributed. The sample mean is found to be x bar equal to 45, and the sample standard deviation is found to be s equal 14. Construct a 90% confidence interval for the population mean. So notice that we're looking at the population mean here. Our sample size is 12, so it was less than 30. If it was greater than 30, we could automatically do a t-interval. But now we need to look for the words normally distributed, and we see that those are there. So since we know that our population is a normally distributed one, even though the sample size is small, we can still do a confidence interval for t.